Let's not beat around the bush. You know you've thought about it, and today we're going to answer it. Would you fart your way through space? If space suits didn't put a firm barrier between you and the outside environment, space would kill you. But for the sake of this episode, let's take some biological license and pretend you could survive without a suit, or if you prefer, pretend you have a suit with a special valve that would allow you to pass gas into the vacuum of space. Would you then propel yourself with farts, and if you could, how fast could they make you go? Before we can analyze the concept of a fart rocket, we need to understand the mechanics of those two ingredients separately, farts and rockets. Let's start with rockets, actually, because there's a common misconception I want to clear up from the start. Rockets do not have to ignite or burn fuel in order to achieve propulsion. An analogy will help explain this. Imagine standing on a skateboard holding something really heavy, like a bowling ball. In this picture, you represent the rocket, and the ball represents the fuel. Now if you push the ball forward hard, the ball also pushes backward on you, giving you and the skateboard a backward velocity in the process. Fundamentally, that's how a rocket works. As it throws fuel in one direction, the fuel pushes back on the rocket to accelerate in the opposite direction. But unlike me, a rocket has no arms. So how does it throw the fuel? Well, in conventional rockets, that's where the ignition comes in. As the rocket's propellant oxidizes, chemical bond energy is released, raising its temperature and causing it to expand until it becomes a gas of particles bouncing off the walls of the combustion chamber. Particles strike the lateral sides equally often, so there's no net push sideways. But along the longitudinal axis, there's only one wall to strike, and the particles push the rocket forward as they ricochet and escape out the open end. But if rockets did have arms, they could just as easily use baseballs as propellant without igniting anything. If you attached 7 million clones of Madison Bumgarner to a rocket and each clone threw 190-mile-an-hour fastball out of the rocket every second, you would achieve the same thrust as the most powerful rocket ever built, the SUS booster that NASA recently test-fired in Utah. So long as you throw enough mass sufficiently fast, it doesn't really matter what you're throwing. So what's all this have to do with farts? Well, think about it. Flatulence is just throwing gas, as opposed to baseballs or rocket fuel, out of your body. Clearly, the resulting thrust is tiny enough not to move you noticeably here on Earth. That's why you don't see patrons at Taco Bell achieving liftoff. The same is true inside the space station. Famed Canadian astronaut Chris Hadfield revealed on Reddit that he had performed his own propulsion experiments on the ISS with no noticeable movement. But in the near-total vacuum of space, expelling gas will have to make you move. In fact, with just a single day's worth of flatus, you could travel the entire Earth distance in only 300,000 years. And that's only if there were no gravity. In truth, even starting out from low Earth order, you'd be short of Earth's escape velocity by a factor of about 1 billion. So, you'd reverse course almost immediately. What's the root cause of this fart rocket fail? Conservation of momentum. After a propulsion event, the net momentum of you and your fuel must remain zero. So your forward momentum must be equal and opposite to the backward momentum of the gas you expel. So how much momentum is that? Let's start with the exhaust velocity of a fart. Fart noise. I'm a scientist, so I would prefer to measure this directly using the wind speed fan. But I couldn't get one, so I used the 3 meters per second value I kept seeing on the internet. Estimating the mass is more involved. You can click over here to see my method of weighing farts. My result was that even over a full 24 hours, an average person produces around 1 measly gram of flatus, and that recoil speed ends up being a staggering 43 microns per second. That's 15 centimeters an hour. 7 meters per day, 26 meters in a week, or 3 kilometers per year. Bottom line, cutting the cheese just won't cut it for long-distance space travel. There's simply not enough mass in your gas. But maybe your space travel goals are more modest. Let's take a different scenario. Suppose you were stranded at rest 10 meters away from the airlock door on the ISS. Did you fart your way to safety shore over a period of about 2.5 days or 3.5 if you actually took a full 24 hours to build up and release that 1 gram of gas, flatulating yourself to top speed in small bursts? And in case you're wondering, sneezing would probably have a similar result. The masses and exit speeds of sneezes and farts should be comparable. I know the internet says sneezes travel at 100 miles an hour, but a study that we linked to in the description used high-speed photography to get an answer closer to 4 meters per second, right around my estimate for the speed of a fart. While we're comparing bodily functions, what about peeing your way to safety? Let's do the math. You can measure the exit speed of a urine stream using projectile kinematics. See the link in the description. Mine was in the same 3 to 4 meter per second range we've seen all episode. Now, since urine is mostly water with the density of 1 kilogram per liter, the half-liter or so capacity of a full bladder would have a mass of about half a kilogram. That's 500 times more than a day's worth of gas. So the net result for momentum conservation about 500 to 700 times higher recoil velocity, a little over 77 meters per hour, or enough to get you back to the IS in under 8 minutes. So peeing looks like the way to go. To pick up comparable speed from farting, you will have to literally break the sound barrier. The required exit velocity would exceed Mach 4 over 3,000 miles per hour, which is over 50 faster than the top speed of the Su-71 Blackbird, and I'm sorry, but no amount of nozzle engineering or blue flaming shenanigans will ever get you anywhere close to that, so don't try it. Moral of the story: if you stick to moving sideways, can technically fart your way through space, but you're much better off peeing. Or if you're still holding onto the 7-layer burrito you had planned to use as raw material, just throw it instead. You'll get more recoil. I hope you found today's analysis informative. Your comments and questions are welcome below. And if anyone is aware of documentable measurements of flatological exhaust speeds, include those too. Let's just say, inquiring minds want to know. Last week I considered whether the moon in Majora's Mask might harbor a black hole. You guys had a lot to say, and we'll get your comments in a second. But first, an encore announcement. This weekend, April 11 and 12, I'll be hosting NASA's Space Apps Challenge at the main stage in New York City. You can attend in person at various cities across the world or virtually online. Check out Space Apps Challenge. Now, to your questions. The Cosmos asked whether gravitational forces are about the mass or density of the gravitational source. Answer: once you're outside the gravitating object, what matters is mass. But how close another object can get before it's ripped apart by the tidal forces due to a first object, which is due to gravitational differentials, that turns out to depend on the density of that second object. Look up Roger limit on Wikipedia. No offense, Fat Lum, Geth Dean, and Parish Danforth all asked in one way or another why the shell of the moon wouldn't collapse and get sucked into the black hole. The short answer is that black holes don't suck. In fact, far from their horizon, which in this case would be just centimeters since the horizon is sub-kilometer-sized, the fact that there's a black hole in play becomes kind of irrelevant. If you have material that's strong enough to withstand internal stresses, you could put a shell that just sits there around pretty much anything, including a black hole. Chronoflect asked whether Termina's moon could actually rip apart in the 3-day window of the game if it were the density of Earth's moon. It turns out that time to disassembly versus time to impact is a pretty tricky issue. A lot of factors come into play. I've seen this modeled in the case of the Shoemaker, Levy comet that hit Jupiter in 1994, but I don't recall whether there's a definitive recipe. I think it depends a lot on the details of the situation. Raphael Viding and Daniel Jenkins asked, wouldn't a black hole as small as the one I'm claiming evaporate quickly in relative terms? Yes. But it would still take 10,000 trillion times the current age of the universe to do so. Finally, Patrick Fajan asked, how can the moon be seen all day long from Termina? You'd seem to need the moon to orbit around the planet at the same rate that the planet spins on its axis, which I agree is not something that should happen if the moon is also gradually getting closer. It's a major inaccuracy in the game, and as I said, I don't have all the answers. Thanks for all the great questions. Keep it up, and I'll see you guys next time.